Okay, in this video, I want to talk about absorption of synchrotron radiation. So if you remember from previous weeks, we said that any emission mechanism must have a corresponding absorption mechanism. Uh, just like, Bremsstrahlung emission had a Bremsstrahlung absorption. So in the same way, there should also be synchrotron absorption. Now, it turns out that unlike Bremsstrahlung, where it's quite common to have thermal plasma, it's quite rare to have thermal plasma that is relativistic. And at least in astrophysics, the reason for that is the mechanism by which charges are accelerated to relativistic speeds usually give a non-thermal distribution of electrons. So you can't simply use Kirchhoff's law as we did for the case of thermal Bremsstrahlung. So you actually have to go through a more complicated derivation to figure out what is the absorption coefficient for synchrotron radiation. So I want to, instead of just giving the final expression, I want to go through that because the technique itself, the formulation that is very generic, and you can use it not just for synchrotron emission. You could also use it for Bremsstrahlung if you didn't have a thermal medium and you could not use Kirchhoff's law. And that formulation actually goes through Einstein coefficient. So even though we are talking of classical radiation mechanisms, the basic idea of there being three types of processes: photoabsorption, stimulated emission, and spontaneous emission, that is fundamental enough that you can apply that even to classical radiation processes. So we would basically be using a quantum description to arrive at a classical absorption coefficient. And I want to present that formulation because it is more universally applicable and it's not just synchrotron absorption. So let's basically relate the quantum and the classical quantities. We did this in some of the problems, so you already have the groundwork, but I want to go back a little bit and make sure that I revise the definitions of the terms. So the Einstein coefficient, the B coefficients, 1, 2, and 2, 1. So this is for photoabsorption and stimulated emission. They're defined in the following way. At least we are going to define it the following way. I mean, there's another definition which you can find in literature related to energy density of radiation, but we are going to use this definition. In the end, you'll get the same answer, but there might be intermediate differences of the order C by 4 pi or something like that. So we're going to define B12 times this integral here as the probability per unit time for absorption, for photoabsorption. Okay, so what's in this integral? So you have the line profile, which is phi nu. That is just, this has units of per hertz. Okay, so that d nu has units of hertz, and in the end, the units of hertz cancel out. So phi nu is the profile function, and j nu here is the mean intensity of the radiation. So it's nothing but specific intensity averaged over all the solid angles. Okay, so that is j nu here. So you can just think of it as the specific intensity I nu, but you have just taken the average value over all solid angles. So that should give you probability per unit time. So this whole thing has units of per second. Okay, so it's probability per unit time. So B21 defined similarly is the probability per unit time for stimulated emission. Okay, so now we can basically try to cast this in terms of the absorption coefficient itself, right? So so check this statement out. So I'm going to say that the total energy absorbed per time dt per volume dv is dt times dv, okay, times h nu, which is the energy of the photons which are being absorbed, an integral over all the solid angles, and basically this expression here, right? So this expression here has units of per unit time, right? And you multiply that by dt, so you get the amount of absorption in time dt. And n here is the number of charges in the lower state n1 and then upper state n2. Okay, so n1 times b12, this quantity here. So let's say if I multiply n here, then I'm going to get the probability per unit time per unit volume, right? So because n is the number of particles which are absorbing per unit volume. Okay, so you can pause the video and have a look at this expression here. So this whole thing basically gives me per unit time per unit volume, the total number of absorptions. Okay, And then h nu is the energy. So I get energy per unit time per unit volume. And then I multiply that by time and volume, I get the total energy absorbed in time dt and volume dv, okay? Now, and now I'm going to basically go closer and closer to the actual definition which I'm looking for the absorption coefficient. Okay, so I'm going to write dv as ds times dA, where dA is the cross-sectional area, ds is the length traveled by the ray. And so what you end up on over here is dt, dv, dA. So per unit area, per unit time. And this is an integral over solid angle and integral over frequency. Okay, so if I now say what is the energy absorbed per unit time, per unit frequency, per unit solid angle, and per unit cross-sectional area, then I'm basically going to get ds, which is left over from dv equal to dA times ds, h nu by 4 pi, and the profile function, and then I nu, and then this whole quantity here. Okay, so what I've basically done is I've basically said what is the energy absorbed per unit time, frequency, solid angle, and cross-sectional area. And the reason why I'm writing it in this form is that energy per unit time, frequencies, area, cross-sectional area, and solid angle is nothing but specific intensity, right? So this is basically the differential change in specific intensity. So basically this whole thing is di nu, right? That's what this whole thing is. So di nu is just equal to the absorption coefficient times I nu times the distance, right? So I've basically cast this quantum mechanical description in the classical differential equation, which involves the absorption coefficient. That's all I've done here, basically. And, I mean, some of this can be confusing, especially if you find different definitions for the Einstein coefficients in terms of energy intensity instead of the mean intensity. So yeah, you might in other literature find slightly different definitions, but in the end you'll get the same answer. So I encourage you to pause the video and then make sure that you understand how we got here. And so from here it's very obvious, right? So if I get rid of I nu and ds, the rest of it must be the absorption coefficient. So here's my absorption coefficient. And yeah, so far everything is generic, right? I haven't really put in any emission mechanism here. Now here is where some of the classical ideas come into picture. So in a quantum mechanical system, the profile function basically is given by the nature of the transition, and there's only one lower state and one upper state, right? So you can either have an atom in the upper state or you can have an atom in the lower state in a two-level system, right? There's just that. But in a classical system, the situation is kind of different. The situation is different because the profile function is more complicated, right? Because you know that in case of synchrotron emission, for example, you have emission over a large range of frequencies, right? So you don't have a very narrowly defined energy difference, which gives photons of a given frequency, right? So you have emission over a large range of frequencies, which means that I need to be a little more careful in basically integrating over all the possible energy levels. So here's one way to write it. So I'm going to sum over all initial and final energy states. So I'm going to call the emission as an event, which takes an electron from energy E2 to E1, okay? And so I'm going to sum over all those possible combinations of E1 and E2, which would give me a photon of frequency nu, okay? And notice here that you can't say h nu is equal to E1 minus E2. That's not a, how do you say, it's not a single atomic transition, right? Because you have electrons emitting over a large range of frequencies. So the way we can take care of that is to have a summation over both E1 and E2, and then make sure that this profile function is defined such that it reduces to a delta function, and it only selects for cases where h nu equal to E1, E2 minus E1. Okay, so this is just, this is probably the only departure from the formulation which you are used to. Yeah, so this would be a classical way to put it, where instead of the formulation of phi nu being a real line profile function in a quantum mechanical sense, we are going to use phi nu to basically act like a delta function and then extend the summation over both E1 and E2. So, that's the only change I've made compared to what you're already used to from quantum mechanics. Okay, so for synchrotron emission, Well, okay, so we basically need B12 and B21, right? I mean, from, you know that B12 is equal to B21. That's just a relationship between the Einstein coefficients. And both of them in turn are related to the Einstein A coefficient, A21s, for spontaneous emission. And we've already calculated spontaneous emission. We actually calculated the amount of energy emitted per unit frequency uh, per unit time by an electron, uh, which is emitting by the synchrotron mechanism. We did that in the last video, right? So all I need to now do is to take what I calculated in the last video, which is power emitted per unit frequency, and relate that to the Einstein A coefficient for spontaneous emission, and basically then use the relationship between the A coefficient and the B coefficients, and then I'm done. I get an absorption coefficient. Okay, so we calculated, I'm going to call the quantity we calculated capital P here. That's the energy emitted per unit time, per unit frequency. Okay, so I'm going to call it P of nu. So that's the energy emitted at frequency nu by an electron that's at energy E2. Okay, so again, remember the difference between the classical and the quantum treatment here is that whereas in the quantum treatment you're used to, an electron at energy E2 can only go in a two-level system, can only go to one other energy state by emitting a photon of a given frequency. But because the emission is broadband in synchrotron emission, an electron at energy E2 can go to a lot of different energies E1, right? So we have to, that's why we have the double summation here. So we can account for all of those transitions, and an electron can go, the photon emitted can be of very low frequencies, which means E1 need to have very small difference between them, or you can have a vast difference in frequency, in which case E1 and E2 will be separated by a larger amount. So that's why we need to take care of all of those possibilities, because it's not a line emission, it's a broadband emission. Okay, so that's something which we have already calculated, and that's just the energy emitted per unit time, per unit frequency. And that's very easy now to relate to the Einstein A coefficient for spontaneous emission. So this has units of per second. It's the probability of emission per unit time. And then I multiply that by the profile function. So I basically get the probability per unit time, per unit frequency, and h nu is the energy per transition. So this whole thing is going to equate to the classical quantity we calculated for spontaneous emission. Okay, so we basically have all the elements here, right? So we know the relationship between A and B coefficients. We know B12 equal to B21. And so we can now calculate the absorption coefficient quite simply. Okay, so I can calculate the absorption coefficient now. I can just take alpha of nu and basically use the relationship between the A and the B coefficient. So A12 and B21 are related, which I've done here. They're related through 2h nu cube by c square. That is just the relationship between the Einstein coefficients, and that's true for any emission mechanism. Yeah, so I can basically calculate the two terms here separately. So the first term is going to be a summation of over E1, E2 of NE1, B12 times the profile function. Now I'm going to use the delta function nature of the profile function, and I'm going to write NE1 as N of E2 minus HV. Okay, so that means that I can bring this out of the E1 summation, and I can go through with the E summation over E1, as long as I write N of E1 as N of E2 minus H nu. Okay, so the E1 summation is basically calculated here, so I just substitute that here. Now the second term, which is this term here, for stimulated emission, is basically going to be, again, it's a double summation E1 and E2, and in this case, I'm just going, the summation over E1 is pretty elementary. I'm just going to use the profile function to say, I'm just going to use the nature that this is a delta, the fact that this is like a delta function, and it's going to only pick out emission at frequency nu, right? And so again, I use this expression here to get rid of the summation over E1. Okay, so I get this basically. Again, you can pause the video and then go through the algebra yourself. It's good to do that yourself to make sure that you understand how we got where we got here. And so that's so far everything is generic, right? I can put the value P here for synchrotron emission. I'll get the absorption for synchrotron emission. I can put any other emission mechanism here. So far, it's all been quite generic. Now, we can go a little further here, which is again going closer and closer to the classical result which we want instead of the quantum mechanical result. And the only sticking point right now is this summation here, the discrete nature of this summation. And the problem with that is we have a continuous distribution of electron energies, right? We don't have a quantum mechanical system where you have discrete energy levels. So we need to replace this summation with some kind of an integration over, let's say, the electron energies or the electron momenta. And so that would be the final step in writing it in a purely classical formalism, is to get rid of this summation and then replace that with an integral over the electron momentum distribution, for example. Now, how would you do that? Well, you do that using the language of statistical mechanics. So you know that this summation should be interpreted as the summation over all the different discrete states in which the electron can be. So in other words, even though we're going to write this as an integral, you know that because everything is quantized, energy is quantized, that integral really is let's say the energy itself is not a continuous function. It has some granularity, and the granularity is given by the Planck's constant, right? So the Planck's constant tells you the smallest cell size which you can have, or the smallest energy quanta which you can have, is given by that Planck's constant. So I'm going to now write this summation in the form of an integral over the distribution function for the electrons. So f of p is the number of electrons per unit real volume in d cube x, and per unit momentum volume, so d cube p, right? So you're probably have encountered this kind of distribution functions in statistical mechanics. So I'm just going to use that formalism here. So here is the last step. So I'm going to replace the summation with this particular integral. Okay, and I'll tell you why this makes sense. The reason for that is 2 over h cube is the number of quantum states in volume d cube p, right? Because because h tells you what is the size of the grid. 2 over h cube is going to give you the total number of states in a continuous volume d cube p. So in other words, if h is very, very small, which means that I make my grid very, very fine, and the size of the grid being the quantum of energy, I would just have if I make h very small and I make the grid very fine, then for a given d cube p volume, I'll have a lot more number of quantum states which can be occupied, right? So if h is very large, it means that the quantum of energy is very large, and the grid is very coarse, it's not very fine, and so you only have a finite number of quantum states. So that's why you have h cube in the denominator here, because as h decreases, the number of quantum states will increase for a given volume d cube p. Okay, so I can again, h is a constant, you can't make it larger or smaller, but I just use the analogy to basically motivate the fact that h should be in the denominator here, right? So just to give you the intuition there. So I can replace that summation with this kind of integral. Of course, there's a 2 here because electron is a spin half particle, right? So you can have 2 electrons occupy one cell, so to say. In the same way, n of E2, right? So number of electrons in the upper level, I can again replace that with the partition function, but now I'm going to multiply by h cube by 2 because this is a density, right? So the end result of this is going to be that the h cubes are going to disappear when you put them together. Now again, you can pause this and think about it for a while, why this substitution makes sense. So again, h is you can think of h as the resolution of the grid, right? So if the resolution of the grid is very coarse, so if h is very large, then for a given distribution function, you're going to have a lot of electrons occupying that particular grid, a given voxel, right, in 3-dimensional space. And if h is very small, it means that the grid is very fine, which means that you'll have less and less number of particles per unit grid point, which is what n is measuring. N is just the the number of electrons per grid per that unit volume h cube. So again, this is all statistical mechanics speak, and I assume that you're at least familiar with this kind of formulation. So you put all of that together, the 2 over h cubes cancel out, and then you get the same thing as an integral. I mean, if you have the intuition, you could just go from this summation here to an integral directly, but you know, it's good to know where the jump comes from. So you just replace the summation with this integral, and again you have a difference here, and that difference now becomes the difference in the distribution function at momentum P2 and at momentum P2 star, which is the momentum corresponding to energy E2 minus h nu. Okay. Now let's just check if we have made some horrible mistake. You can always do that by putting in a thermal distribution, in which case you should get back Kirchhoff's law, right? So for a thermal distribution, f of p is some constant c times e to the power minus energy corresponding to that momentum divided by kt. So f of p2 star minus f of p2 is basically going to be this here. So I can take a common factor, which is f of p2. I can take that as a common factor, and I'm going to end up with e to the power h nu by kt minus 1. Okay, so if I put that into this integral here, then I'm going to get this expression here. And notice what this integral now reduces to. So this is nothing but the energy per unit frequency and time and volume, right? Because P here is the amount of energy per unit time, per unit frequency emitted by a single particle. And now I'm going to integrate over the entire particle distribution function. So when I integrate over all the momenta, so remember that F integrated over all the momenta has units of per unit volume, right? So because F is defined per unit volume in real space and per unit volume in momentum space, and you just integrate out the momentum volume, you'll be left with per unit volume in real space. So this whole thing will be the energy emitted per unit frequency and time and per unit volume. Now the only thing missing is per unit solid angle. So let's say you have, the bulk, let's say the emission is isotropic. So a single electron's emission is not isotropic, but let's say that the electrons are oriented with all possible pitch angles, so you'll get isotropic emission. So this will be 4 pi times the emission coefficient. Okay, so you put that in, and you know, this is now beginning to look like Planck's law, right? So this basically reduces to, the Planck function, and so this basically reduces to Kirchhoff's law. So it all makes sense. Now, if you also have an isotropic distribution of electrons, you can get rid of this 3-dimensional integral over here and just make it into a 1-dimensional integral of energy, let's say, because you know, if the electrons are moving in all possible directions, then you can always get rid of the 3D integral. So you can, instead of a 3-dimensional distribution function f, you can have a 1-dimensional distribution function n of e. So this is the differential number of electrons per unit energy interval. So you know, you can have this substitution where n of e dE is nothing but f of p 4 pi p square dp. Okay, so this is just going from a 3D momentum distribution to a single, to let's say 1-dimensional energy distribution. And notice that I can only write this if energy is equal to Pc, or in other words, energy and momenta are linearly related, right? So notice that I haven't put any Jacobian here. The only Jacobian is dE, which is the differential element, and 4 pi p square dp, which is the differential volume element. So if you don't have this simple linear relationship, of course, you can't do that. So I'm going to assume that the particles are all ultra-relativistic. So energy is equal to Pc for ultra-relativistic particles. So then I basically get everything. Again, you can pause this and go through the algebra yourself. I've basically skipped a couple of algebraic steps here. So you get the absorption coefficient now as a single line integral over energy dE. Okay. Now here's the last trick, so to say, and then we are done. Now notice that I think we've done this several times in the course, where we said that for the radiation mechanisms we're dealing with in all practical cases, the particle loses a tiny fraction of its kinetic energy, right? It's not like the particle can instantaneously lose all of its kinetic energy. The amount of energy carried off in radiation is tiny compared to the kinetic energy of the particle. So this difference here, which is n of e minus h nu minus n of e, right? The difference in energy, so h nu is going to be far, far smaller than this energy e. So this difference here can be cast as a derivative, right? Because h nu is such a small quantity that this basically can be cast as a derivative without making much error, right? So because h nu is far, far less than E, I can basically write the whole thing as a derivative. So this is nothing but a derivative with taken over a difference equal to h nu, right? So this would basically be d partial derivative with respect to energy of this quantity here, which is n of E by E square times h nu, right? Because the derivative is taken over a difference h nu, right? So one factor of h nu basically cancels out, and then you get this expression. And also notice the minus sign here because there's a minus h nu here. So that is the absorption coefficient, which you can use. So this, remember that this only applies for ultra relativistic particles, which are which have an isotropic distribution, right? Otherwise, we couldn't come to this step here. So the kind of formulas to remember, which are generally applicable. This is generally applicable, right? For any radiation mechanism, this is applicable. This formulation is also applicable for any radiation mechanism. So so I would say this is the most generic formula, right? This applies for any radiation mechanism. You can put in any prescription for capital P here, that function, and you can put in any particle distribution here, and this would basically apply to any radiation mechanism, right? And so the only particular things which we did, which is related to the isotropy, isotropy of the distribution. So if the particle distribution is isotropic, then you can come all the way here, right? So that would be the absorption coefficient. So this is basically a quantum mechanical formulation to calculate the absorption coefficient of a classical process. So you can again check here. So over here, you can put in a thermal relativistic distribution of particles, and you should get back Kirchhoff's law. Maybe we'll do it as a problem, but I wanted you to know the way you formulate this problem, because you can apply it not just to synchrotron emission, but for any emission mechanism. So it's a very powerful formulation to get at the absorption coefficient of classical emission mechanisms.